Well, good morning. There was some homework that was due this morning. Hopefully, that wasn't anything too terribly challenging. The homework was to take the little start.hex file, which I made available on iLearn, and do some stuff with it. Get your Linux environment ready. So this is sort of the test to be sure that things work. Figure out what XXD does, and what it does is it converts things to and from hex dumps. Turn that little file into an executable and run it. Since I told you about XXD and the file contained hex, seems like the thing to do would be to try to use that to turn the hex dump back into a binary file. That gets you a file, but it doesn't get it runnable. So then you have to do something else to make it runnable. And then save the output and upload that. So let's pop down here for a moment. There's a little start the hex file. And the trick is, of course, XXD has normally would be generating a hex dump. So if I just ran XXD on start.hex, it would dump out that in hex, which is kind of hilarious. What I want to do is reverse that, and that's a -R, and then give it start bin, or any name you want, I guess. And now we have start bin, which is a little ELF file, a 32-bit ELF file. So can I run it? No, I can't. It says permission denied. Why is that? It's not executable. So I make it executable. Now can I run it? And I can. And so I run it and I dump the output to start text. And I'm upload start text and I'm done. The only issue you might have had is if you were trying to do this under the Windows subsystem for Linux on an older version of Windows. It didn't give me any trouble on Windows, on the newest Windows, but on my other machine, which is running Windows 10, it gave me some issues. But this could be done, as I think I said, this could be done on the Tennessee Tech machines, and it would have been just fine as well there. So I also mentioned that you might want to try objdump. And so let's just try objdump -d m intel start text, see what's going on. And it says file format not recognized. Let's try, I think it's dash S. No. Headers? Wow, it just doesn't recognize the file. So
is it because you're doing it on start text and not the binary?
Oh, it is because I'm doing it on start text, not the binary. Let's go back to bin. Thank you. And format not recognized, and S and H. There. So I was getting the answer I expected. I was just getting it for the wrong file. So it doesn't recognize the file format. This thing seems crazy, and yet it does in fact run and work. So what's going on there? Well, in a later class, we'll talk about the ELF file format. When we do, I will post an explanation of how it is that start.bin works, because it kind of abuses a lot of the standards on the system, right? Again, most things on a machine are done by convention, and because of that, you can often ignore the convention, and start.txt ignores a lot of the conventions. All right, it's kind of a fun little file. Tools. So today, the tool is the bashrc.sh script that's available on iLearn. And this is just a script that works with Bash and Zeesh. It adds some stuff to the shell. Dis, vdis, dism, vdism, mk. So I could say dis of which ls, and it would disassemble it for me. I can say vdis, and it's hard to see here. What it does is it adds these little jump indicators, and some of it gets nested pretty deeply, and so it kind of just be a mess. There's also ones that automatically send you to a pager, and it figures out which pagers you have on your system. So I have most installed, so it uses most for me here, etc. So those are kind of neat. But more importantly, it adds this little guy, make, which if you've noticed the tops of some of the listings, they have this little make thing at the top of them. Instead of building a make file, or instead of doing something else, I decided that the correct solution was to write a really complicated bash script that uses that first line to build things. And so it pulls off the text after make, does some variable substitutions, and then executes whatever results, and builds it that way. So a lot of them with this, that just says assemble and link using LD, or assemble and link using GCC, and it could be just a straight up command or whatever. So I'll be using that. If you want to use it, you can download it, source it in your Bash RC or your ZSHRC, and you're good to go. All right. Assembly. I keep promising assembly. Let's get into it. There are a lot of different assembly languages out in the world, and they have a lot of things in common, and then they are very different from one another. So each processor has its own machine code, and therefore it's going to have its own assembly language. If we have a sequence of bytes like 08 eFox90, then we look at it on disassemble it on an x86 64-bit machine. We'll see that we're ORing together two 8-bit registers, and then we're doing a NOP, a no-op. If, on the other hand, we look at it on the Motorola M68 HC11, I think it's a coal-fire line of processors, we'll see that 08 is incrementing the index register X, and E590 is doing this little bit thing with. Sorry, my son's getting a bunch of text messages on his phone down here. Doing a little bit test on it. So clearly different machine languages. There can be different dialects of assembly language. The x86 has two dominant ones. They are the Intel syntax, which you see over here, and the AT&T syntax over here. And the Intel syntax is the one that shows up in the Intel manuals. It shows up in almost every platform where this is used. The AT&T one is the one that shows up in the GNU tools on Linux. That's about it. In fact, a lot of other tools on Linux don't use this format. They use the Intel format. So we're going to use the Intel format here. It tends to make some things maybe a little bit more explicit. We'll see that as we go along. But you will see both, and you might as well get accustomed to the idea that there are two. So over here it's sub RSP and 8. Over here it's sub 8 and RSP. So some things are just very different. If you're seeing dollar signs and percents and that kind of thing, you're looking at the AT&T syntax. Each assembler has its own directives, its own macro language, and then there's specialized syntax for different things. And that's true for each disassembler. And that's not very unusual. I mean, different compilers can have different pragmas and other kinds of things that work in them. So here's an example where I've got a listing, a short hello world listing. It's over here and it's set up for NASM. And over here, I have hello world set up for the GNU assembler. And I've told the GNU assembler I want to use the Intel syntax without prefixes. The prefixes are a whole thing in the GNU assembler, but I don't want to use them, so turn them off. Intel syntax, no prefixes. And now they begin to look pretty similar, right? There's main, push, RSP, so on. Looks pretty much the same, but there are still differences, right? Look at this. Load effective address, RDI, rel message. Over here, it's message plus RIP. Call putf with respect to the PLT. Call putf at PLT. Okay, interesting. The directives are different. Global main and extern putf becomes dot global main and dot extern putf. Section text becomes just text. So even now that they're using the same dialect, they still look very different or have some differences because there's different implementations. If I go ahead and actually take the code in both those files and assemble it and object up the result, look at this. Byte for byte, they produce exactly the same thing. That's kind of neat. In fact, I think they're both down here. Use that little make script, make type nasm.asm and make and take a look at the two files. There's the binary for one, 16,536. There's the binary for the other one, 16,536. Same length, but they're not the same exact file. There are slight differences in how things get laid out inside the file, but they both work. And the slight differences have to do, I think, primarily with relocations. We'll talk about that later on. So there's a lot of common stuff. Because there are lots of different machine codes, there's a lot of different machine languages. But over the years, they've tended to converge. People have borrowed from one another, and we've sort of converged on a set of things that are common across them, right? These machines operate in a fetch, decode, execute cycle. They didn't always do that. In fact, early machines didn't have a notion of a fetch, really. They just sort of executed a series of instructions hard built into the processor. There's an instruction pointer, also called a program counter, that determines the location of the next fetch. Again, some very old machines don't do it that way, but all the modern ones try to do it that way because it solves a lot of problems. Control flow is handled by conditional relative branches or unconditional jumps. There's a simple subroutine system. Typically what happens is the return address is pushed on the stack or it's held in a register until a return instruction is executed. And that's how you make little subroutines work. There are registers. There are some machines out there that don't have many that really focus on the stack, but there are fewer and fewer, and they still have to have an instruction pointer. There's a stack, of course. Programs directly reference memory. There's a condition register with flags, and these kinds of operations, rotating, shifting, and bitwise operations, those are really, really common. Like I said, the program counter and instruction pointer always point to the next linear instruction. That simplifies things. It simplifies calling and returning. Not everybody does it that way. The 6502 processor used in the Apple II, and I think the 6510 was used in the I think that was used in the Commodore 64. It has to waste some cycles because it doesn't do that. it stores the program counter on the stack, but it's off by 1 when it stores it, and it has to increment it when it returns. It's a common convention that the stack pointer will point to the last item pushed onto the stack. Not everybody does it exactly that way. 6502 doesn't do that. Instead, it points to the first open address. So basically, it stores and then decrements, as opposed to decrementing and storing. Turns out there's some good reasons to do it the other way. And this is all based on the usual convention that if you have two possible addresses for a thing, right, the last item pushed or the first open spot, the higher address is often chosen, and that's true because it tends to be aligned. Right? The low bits are 0. Memory alignment will turn out to be a really important thing, especially with the stack. We'll talk about that in a later class. But basically, you tend to move toward the higher address. A lot of common elements. Instructions follow a basic format. There's a mnemonic, which is a fun word, but many of these are easy to remember and fairly obvious. A lot of them, because there are just so many, become really obscure and you have to sort of look them up. There are operands. So operands is the term that we use for explicit arguments that are given right after the mnemonic. And here there are two. There's a register, RAX, and there's a literal value, in this case, 1. Here we have two explicit arguments, but there can be implicit arguments as well. The order of operations matters. Your L values tend to be on the left. Your R values tend to be on the right. And that's the way nearly everyone does it, with the exception of the AT&T format that reverses it for, I guess, reasons. So this little guy is the move instruction. It copies information. And so it puts the value 1 into the register RAX. And it's probably the most commonly used instruction on the x86 platform and the ARM platform and many others. So the Intel operations typically have 0, 1, or 2 operands. There's a few like IMUL that can have 3, and they can be explicit or implicit. So the first instruction here is the clear carry. This clears a flag in the flag register called the carry flag, sets it to 0, and it has no operands or arguments. The next one is a return, and it can have 0 operands or it can have 1. And for the rest of this class, I think, and except for maybe one special example, it will only ever have none. It'll just be return. The argument to return is something that you will see if you look at older 32-bit code, and it has to do with manipulating the stack. And you can still do that, but you're not going to. Increment has a single argument. That's the thing you increment. So it has 1 parameter. Add here has 2. This adds the value in EAX and the value in EBX and stores it in EAX. So again, the L value is on the left. IMUL can have 1, 2, or 3. You can look that up. It's kind of fun. So can mul can only have doesn't work the same way. It can only have 2. So IMUL, which is assigned multiplication, this one multiplies EBX by 7 and stores the result in EAX, and it's signed. And MoveSB doesn't have any parameters. It actually has 3 arguments, but they're all implicit. All right. So wide variety of stuff. So In some cases, disassemblers will show the implicit arguments as if they were explicit operands, and you can change them. So when I do this move SB and I assemble it, and then I go and disassemble it, it might show me this. Move S, byte pointer ESRDI, byte pointer DSRSI. This is the destination register. This is the source register. And I cannot, in fact, change them. Won't assemble because it's just not the way it works. This is how it works, where the registers are implicit. All right. Some of them take this to the point of borderline madness. Every assembly language has some weird stuff about it, and x86 has most of the weird things you can have. A good example of this is the division operator. So here's division. I say div RBX. Well, I have to have two things to divide, and it turns out that what I'm actually dividing is RDX, RAX joined, so a total of 128 bits. I'm dividing a 128-bit number split across two 64-bit registers. And I'm dividing that by the 64-bit number in RBX. And I will store the quotient in RAX and the remainder in RDX. Wow, lots of stuff going on there. And in fact, when I perform this division, the entire quotient has to fit in RAX. If it doesn't, and there's still something left over in RDX, I get a processor exception. So division is another fun, weird example. And the only thing I get to specify explicitly is this. RAX and RDX are implicit. So this has one operand, two arguments, right? The dividend and the divisor, and uses three registers. It's just fun how this stuff works. There are different ways to specify an operand. We call it the addressing mode. Some processors have lots of fun and fancy ones. The x86 has 4 high-level modes. Now, if you go elsewhere, you'll find them maybe specified different ways. Really, there are 4. There is the immediate, where I just give you a value, like 7. There's register, where I give you a register, like RAX. I can give you a memory address, and there are different ways to specify it, and we'll cover that. Or I can specify one relative to the current value of the instruction pointer. These last two look the same, and they get lumped together sometimes, but they don't actually work the same. Okay. Here's an example of an immediate addressing mode for an operand, just a number, in this case in hexadecimal. Here is a register. Here's a memory reference. I take the address in RDX and I add 16 to it. And then go get the contents of memory at that address. Here's the RIP relative. I take the address of message with respect to the instruction pointer, and I go get the contents of that. So that's how that works. All right. You have a lot of tools when you're trying to write assembly. You have operations that you can use. There's tons of those. Registers, memory, stack, there's conditional branches, and there are unconditional jumps. And that's pretty much everything that you have in terms of programming tools to get the job done. You don't have a lot of control flow stuff. There's no while loops or if then else's. You kind of have subroutines, but not really in the way you maybe used to. There are no complex data types, and there are no objects. You can build all these things from the Lego pieces that the processor gives you. I mean, that's what it does when it compiles your code. But you have to build them. Assembly languages are sort of the language. They predate high-level languages, but they have also adapted to the needs of compiling high-level languages. And the primary focus has always been improving the overall performance. And there have been some big influences on the way that modern assembly languages look. RISC has been one. Even though we're not on a RISC processor, it's heavily influenced by what's been done with RISC, which is the major competitor to the x86 type of processor. It's been influenced by programming languages. Three highly influential programming languages are BCPL, C, and C++, which have undoubtedly influenced the way that the processor works. Vector operations are increasingly dominant, and so we keep having to add larger registers and vector operations to the processor, and so that's had a big effect. The objective function, the thing we're trying to optimize the processor for, tends to be performance, not readability, maintainability, compatibility, or usability, right? Assume you're going to write in a high-level language and use a compiler, which is the easiest way to produce assembly language. But as a result of that, they sacrifice a lot of the properties you'd want to have in a programming language. And they're not necessarily looking for code performance. It's usually, can I compile your code really, really fast? Lots of concerns to balance here. There are two dominant instruction set architectures at a high level. One is the CISC, or Complex Instruction Set Computer Architecture. The idea here is I want to have a very rich set of instructions. They may do very complex things. Some of them may take a long time to execute, but that's okay. They're doing lots of work. They tend to vary in terms of length. So there's how you know that x86 is one. It has single byte instructions all the way up to 15-byte instructions. And there are lots of examples. The Z80 and the x86 are both very popular processors that are CISC processors. And then there's RISC. So RISC came along a little later, and the idea was we're going to have a reduced instruction set, and each instruction will do one simple task. And I want them all to execute, if possible, in a single clock cycle. So programs may get longer because they don't have these complex instructions. And there are lots of examples of that too. The RISC-V is one, the ARM is one. And one nice thing is, in terms of pipelining and fetching, instructions are all the same length. A downside to things like ARM is, for x86, I can load a 64-bit value into a register using a single instruction. And that's great. I can't do that in 64-bit ARM. Instructions are all a single length, and that length is not long enough to fit a 64-bit literal in it. So I have to play other tricks to get a 64-bit value into a register. Here are some references for you. The first one we're going to use a little bit today. It's a good way to look up what instructions are and what they do. You can also go to the official documentation. I find it to be maybe a little harder to use once you get familiar with what's happening, but it's there and it's certainly useful. There's an online disassembler that's good to use. You can upload chunks of code and see what the online disassembler makes of it. You could upload start.bin and see what the online disassembler makes of it. There are some online IDEs that use NASM. There's one here. Ray Chapman has a nice post that lists the system call table for x86 64-bit Linux. And if you want all of them, the Chromium OS has one that has it for ARM and a bunch of other processors as well. The point here is that learning one assembly language well, and I will say especially one that is as complex as x86, will get you ready to learn any assembly language. I think you'll find that if you learn x86 and then later on you have to learn ARM, you will think, oh, this is really simple, because you really have all the receptors in your head, and ARM is in many ways much nicer than x86. So let's talk about writing assembly. Writing assembly is going to help you better understand and improve the way you write plain old code, because again, it's going to influence the way that you write like C code, and that's going to have some good effects. But you're going to be able to read and write assembly. That's going to be good because when you see people at Black Hat or DEF CON or other places, often they'll be talking about assembly and disassembly. Sometimes reverse engineering benefits from making changes to a compiled program or modifying it. So even if you're trying to live in the world where you're looking at decompilations, you're still sometimes going to have to modify a program, and you have to modify the machine code itself, and you'll have to do that through assembly. And it's fun. The instruction set architecture. This is a very high level view of what programming on this looks like. You've got a processor, you have some general purpose registers on the processor, you have operations that you can perform, so things like add or sub that connect the registers to the arithmetic logic unit and then connect back to registers. You have a flags register that gets set based on what happens. Usually this is stored, this is sort of logically inside the ALU, but that's what's on the processor. You have some special registers, the instruction pointer and the stack pointer that live inside here. The instruction pointer points down here to the next instruction in the program. The stack pointer points to the last thing pushed on the stack, the lowest address used by the stack. And then you usually have a program at low memory and a stack at high memory. You don't have to. By convention, I could swap those and things would work, but that's usually how the operating system will set things up for me. In addition, the operating system will set up something called the program break and provide me with a heap, and I can use that. So this is how things will normally look to you, because you'll be writing code on a machine with an operating system, and these are the things, this is the way that programming will look. The x86 has grown over the years. It started out as a 16-bit processor, and it had a little series of registers: an accumulator, a base register, a counter, a data register, stack pointer, a base pointer, source and destination, indices, and an instruction pointer. And they were all 16 bits. And you could actually address, for the first four, you could address the high bit or the low bit directly. So AH was the high bit of the 16-bit AX. AL is the low bit of the 16-bit AX. Or the low byte, sorry, low byte. So there you go, bytes and words. Time passed and we decided we needed 32 bits. That's 4 gigabytes, which should be enough for anybody. And we added some registers. The extended AX, BX, CX, and DX, the extended stack pointer and base pointer, the destination and source indices, and instruction pointer. These are all typically going to be holding addresses. Since addresses are now 32 bits, these all had to be 32 bits. The older registers are still around, but they couldn't hold a complete address anymore. We had some aliasing. We could think of EAX as 16 bits and AX. AX is still around. It lets you access the low 16 bits of EAX. And AH and AL are still around. So we had bytes and words before, but now we had double words and tend to call those D words. So time passed and everybody was happy and no one complained about anything. But then people like Apple really wanted 64 bits, and along came a couple different 64-bit architectures. And the one that sort of won out was the ARM version. The Intel version of the ARM version is almost exactly the same. There are some obscure differences between 64-bit ARM and 64-bit Intel that we won't go into, but they're almost exactly the same. So here R is for register, and we have RAX, RBX, CX, DX, and so on. So these are now 64 bits. And so the stack pointer, the base pointer, the instruction pointer, those are addresses, so they have to be 64 bits. So ESP and EIP are no longer the stack pointer and instruction pointer. They're just the low 32 bits of those registers. So if I want the low 32 bits of RAX, that's EAX. The lowest 16 bits is AX. Byte 0 is AL and byte 1 is AH. So there's different ways I can alias it. In addition, we added some new registers. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 of these, but this one really doesn't count. So there's really 8 of these. We call those 0 through 7. And if we do, then we have 8, 9, 10, 11, 12, 13, 14, and 15. All these nice additional registers to use. That's great. So now we have 16 general purpose registers that we can use. We added, of course, a quad word, which we can call a Q word, to it. There are additional registers on there as well. There are 80-bit floating point registers. If you look down here at the MMX piece, you'll see it has 80-bit floating point registers and 64-bit MMX registers. So the 80 bits is here. If I want to reference just the first 64 bits, they're overlaid, just like with EAX and RAX. In addition, there are 128-bit XMM registers, and there are 16 of them that I can use. There are segment registers still on the processor. If you don't know what segment registers are, that's fine. You're not going to need to know for this class. There's a code segment, data segment, stack segment. There are some others that got added with the 386 processor. If you wonder about them being used, you can go and read about these tables, especially the global descriptor table. If you're building an operating system, you have to think about this. If you're not building an operating system, you don't have to think about this. Some people like to say they're not used anymore. Then why are they on the processor? Right? They are still used. For example, you can see the privilege level in the bottom 2 bits of these. Okay. But for the most part, you can ignore these. There are some tricks you can use if you can manipulate these, but and maybe we'll cover that later on. It depends. There's flags. Carry is just an arithmetic carry. When you were adding numbers and you had a carry, that's what the carry flag essentially holds. When I'm adding two binary numbers, my carry will be a 0 or 1, and I store it in the carry flag. When I'm subtracting, I might have to borrow. If I have to borrow, I set the carry flag. Pretty simple stuff. The parity flag tells me something about the low byte and whether its parity is even or odd. The auxiliary flag is basically, it's weirdly still there, but it's not really easily accessible and it's not really used. So you can pretend it doesn't exist. It was used for something called packed binary coded decimal that we will not use. There's a 0 flag that tells you if the result of the last instruction that set the flags was 0. A sign flag that tells you if it was negative. There's a trap flag, which we'll talk about when we cover how GDB works. There's an interrupt enable, a direction flag, which has to do with string operations and the way in which we copy memory. An overflow flag, which is just what it sounds like. If I do an arithmetic operation and the result overflows the register, I get the overflow flag set. And then there's a 2-bit privilege flag. We went to 32 bits. We added some more flags. Zoom, virtual 8086, alignment check, virtual interrupt, interrupt pending, the CPU ID, and the virtual address descriptor. When we went to 64 bits, yes, the flag register became a 64-bit register. So up here are the original flags. Here's the extended flags that go to 32 bits. And then here's our flags, and they're just not used yet. They're reserved. How do you get access to it? You can't directly access it, but you can. There are tricks to get access to it. Push F will push the flags register onto the top of the stack, and Pop F will load the top of the stack into the flags register. So once it's pushed on the stack, I can access it by accessing the stack, manipulate it, put it back on the stack, and then use Pop F to put it back in flags. And you might want to do that for certain special things like setting the trap flag. There's not an instruction to set the trap flag or to check it. And so to do that, you have to play this game of modifying it, something like this. There are ways to get to E flags and R flags, and they are push FD for double word and push FQ for quad word. In addition, if you just want the low 7 bits, and that takes you up to the sign flag. It omits trap and others, but it gets most of the ones that you might want. There is load AH from the flags, which loads the flag bits into AH, which remember is the second byte of RAX. And there's save AH into flags, which moves AH into the flags part of the register. So there's going to be lots of overlays here. Special registers. RIP is the instruction pointer. You can't directly modify it, but you can use RIP relative indexing, and there are tricks to get its current value of RIP. It's not really a general purpose register. It's one used by the processor to say where to go next. So it's not always a good idea to directly manipulate it. But if you're creative, you can. Stack pointer, you can do whatever you want to with it. You can modify it by adding to it, subtracting. You can load values straight into it. It's a general purpose register. But again, it may not be the best idea to do that. The base pointer is a general purpose register that is usually used to hold the address of the base, or the highest address, of your current stack frame. So we'll talk about stack frames later on. So RBP can be used that way, and it often is, but it doesn't have to be. There's nothing special about it. And you could actually use a different register for in place of RBP. Just by convention, we tend to use RBP as the base pointer. RCX is the count register. It has some special properties that other registers don't have. There are some special instructions that work just with RCX that work with it implicitly. And so we'll talk about the loop instruction. It uses RCX. There are some special conditional branches that check RCX for you. But otherwise, RCX is just a general purpose register. If you're not doing those things, you can use RCX for whatever you want to use it for. The source and destination registers, same thing. They are implicit arguments to certain instructions, but otherwise, they're just ordinary registers. All right. Enough of that. That's a lot of high-level information. Let's go through a fairly small example. And I recommend you go through this just to be sure that you can assemble and link assembly code in your environment. Simple assembly language program. We're not going to go too in depth into what it does. We'll save that for the next example. All this does right here is starts up and exits. It uses the exit system call. We'll talk about system calls in a later at a later time. Don't worry too much about that right now. So here it is. This starts up and it returns 0. That's it. ex1.asm. There it is. If I say make ex1.asm, it gives me a warning. It says it cannot find symbol _start defaulting to this thing. Okay. Did I get ex1? I did. And it returned 0. So that worked. And this is how, if you didn't use make, you would just use NASM. You'd have to tell it, I want a 64-bit ELF executable. It would build that for you. If you then did an obj dump of it, you'd find out that it had in fact built you a 64-bit ELF executable for the x86 platform. And it had turned your code, your assembly source, into machine code over here. So there are the actual bytes that will be used. It gives you an offset for each of these. So this is location 0 in the text segment. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. So there you go. And you use an offset in hex. By default, almost all these tools are going to dump out stuff in hex. They won't always tell you it's hex. We see that this is in something called the section.text. If you don't specify the section, text is used. We'll talk about sections a little bit later on in this class. When we link it, we get a warning that you saw. Can't find entry symbol start, defaulting to this. So assembly took this stuff and turned it into machine code. Linking tries to link together parts of programs. It tries to identify addresses and connect them up, right? This doesn't have any addresses assigned to it, and it doesn't until such time as we link. When we link, things get assigned addresses. And once you know the addresses of things, then you can link procedures together. Well, the only thing the linker needs to deal with for this little tiny program is the entry point. What's the first instruction to execute? Well, it's this one. And so the way that it does that is it looks for a symbol called start. If it doesn't find one, it assumes the first thing in here is the first instruction to execute. And in our case, that's correct. Now, what is this thing? We'll talk about that later. We get executable, we can run it as you saw. We can look at the executable file with obj dump, and we will see that funny number again, right? Remember from the warning, we had this little guy, it said defaulting to that. And here we see that that is in fact the address that got assigned to the first byte of the first instruction. So that's actually the correct entry point, and that's great. So we can make things a little better by going ahead and adding a label. So a label gives a symbolic name to the first byte of the following thing, whether it's data or instructions or whatever. So start, just like a label in your C program for GoTo, is a label for the first byte of this move instruction. So now we have underscore start in here. That's what the linker wants. We should be in good shape. So we link and it says, cannot find entry symbol start. What? It's right here. It's right here. Well, it turns out that in C, you can make symbols private by making them static. You may not know that there's modules. C is a modular programming language. And to make something local to a module, or therefore private, you mark it static. Otherwise, by default, things are public. Well, in assembly, by default, things are private. And so to make it public, we need to use global for that. So we need to declare start to be global. And so if we go back and do that now, look at that. No warnings of any kind. When we link, we can run it and life is good. So these little guys, arbitrary symbols that you can use to specify parts of the code. You want underscore start. There it is, globally defined. That's the default entry point for the linker for Linux. It's going to be a little different on other platforms. It's a little different on the Mac. It's a little different on Windows. It's the same on Linux on ARM because it's still Linux. Let's go through a larger example and let's actually walk through each piece of it. And we're gonna build an assembly language program. So if you remember in lecture 1, there was this funny sequence of numbers. if the number was even, we divided it by 2. And if it was odd, we multiplied it by 3 and added 1. This was the sequence that we don't know if it always terminates, but we do know it always terminates for all the values we've checked. And we repeat till the number reaches 1. The stopping time is the number of steps it takes to reach 1. So for example, the stopping time for an initial value of 3 turns out to be 7, right? 3 is odd. 3 times 3 is 9, plus 1 is 10, which is even. Gives us 5. Times 3 plus 1 is 16. Divided by 2 is 8, then 4, then 2, then 1. There's 1, 2, 3, 4, 5, 6, 7 arrows. There's 7 steps. And so the stopping time for 3 is 7. And so let's write some code that computes the stopping time of a number. We're not going to deal with reading and writing stuff. We're not going to deal with the arguments. We'll just hard code the numbers for now. So for odd numbers, we have to multiply by 3 and add 1. x86 has a mul instruction that takes one explicit operand and uses RAX as the other implicit operand. It's very similar to the way that div worked. The product is stored in these two. So a 64-bit register times the operand, that could be bit more than 64 bits. The overflow goes into RDX. So if you had something in RDX and you do a mul, it's going to override it. So just be aware of that. It's not mentioned there. It's implicit, but that's how it works. So to make this work, we'll need to put a value in another register, because I can't just say RAX. I can't just say mul 3. It won't work. I have to use another register with mul. So I have to put 3 in a register, like let's use RBX, and then I can say mul RBX. When I say mul RBX, it'll take the contents of this register, multiply it by the contents of RAX, store the result in RAX with any overflow in RDX. A lot going on there, but this is what it looks like. I move 3 into RBX. I multiply RAX by the 3 that I just put in RBX. And now I want to add 1, which is really easy. I just add RAX and 1. Here's my multiply by 3 and add 1. This assumes a few things. It assumes that the initial value is in RAX. So I'll need to be sure the value I'm keeping track of is initially in RAX. When I'm done, the new value is also in RAX. That's fine. That's what I need to do. If you want to know more about these guys, you can look here. In fact, we'll pop out and I will find the mul. Lots of instructions. Lots and lots of instructions. This is not all of them, but it's a good number. Let's move. Move comes in a wide variety of styles, very flexible. And there is mul. So mul, if you were hand assembling it, you'd need this. You're not, you don't need this. It has, so mul can take a register or memory, RM is register in memory, and that could be 8 bits, 16 bits, 32 bits, or 64 bits. In our case, they are 64-bit registers, and it performs the unsigned multiply. And you see here, it's whatever the operand is, the register of a 64-bit memory, times RAX stored in here. So there's all the implicit stuff we talked about before. And it sort of walks through it, gives you lots of information. Again, this is pretty useful once you sort of know the gist of what's going on. All right. Let's get back to this. Whoa. Well, maybe we can get back to this. There we go. That's what we're looking for. So for even numbers, we just need to divide by 2. And so how does that work? x86 has a div instruction that takes a single explicit operand and then has these other 2 registers make up the second operand. Okay, that's great. Since we know the thing we want to divide is in RAX. All we have to do is put 2 in RBX and divide. So there we put 2 in RBX, div RBX, and the result is in RAX, so we're done. This divides RAX by 2. But why do we have this? We have this to prevent the possibility of a processor exception. Remember, it's dividing this 128-bit number. If the result doesn't fit in 64 bits, the processor will throw an exception. If there's some left over in RDX, it'll throw an exception. So to prevent that, we put a 0 in RDX. So now it's just a 64-bit number we're dividing, and we won't get a processor exception. So we need that. Just a quirk of the way div works. You can take this out and see if you get an exception. How about the and if then else? We want to test if a number is even and then do one of those 2 different things. So to test if it's even, we need to divide by 2 and see if the remainder was 0. Now, the remainder is going to be in RDX. So we'll have to go look at that. So let's see. We're gonna divide it by 2, but if we divide RAX by 2, we've messed it up. So what we really need to do is save it and then restore it. So let's put 2 in RBX, 0 out RDX, so don't get an exception. Let's go ahead and save RAX. We'll move it into RCX. We're not using it for anything else. Let's use it to save RAX. Then we do the div, and then we can restore RAX from our temporary variable. So we save it temporarily here, restore it here. We do our division here that divides it by 2. That's what's in RBX. And now the result of that division by 2 is in RAX, and the remainder is in RDX. All right. What about this move? Doesn't it mess up the result of this? It does not. Move doesn't change any flags, but that's okay. We don't need the flags. We just need to check now to see if RDX is 0. So we do that. We compare RDX as a CMP instruction that compare RDX and 0. And then we jump if they are equal. So jump equal to even. So here we go. We divided by 2. We look at the remainder. We see if the remainder is 0, meaning the number was even. If it is, we're now going to jump to the label for even. And that's right down here. So the stuff we do in the odd case, the code we wrote earlier that was times 3 plus 1, that'll go here. The code that we do in the even case, the divide by 2, that'll go here. We made sure we didn't mess up RAX, so RAX is still the correct value. And then we do that little piece of work. So we substitute in the cases. There's the odd case, and here's the even case. We have a minor problem. Control flow is going to just flow right down through these. Hit this. We might jump to even and do these, or we might not. We might do the odd case and just plow right through all of this. We don't want to do that. We don't want this case to fall into this one. So we need at the bottom of this to jump over this. And so we'll add a label. We'll call it over, and we'll just jump over it. There we go. So here we go. We come down through here, do the comparison, jump to even if it's even, do the divide by 2. If it's odd, we don't do the jump, right? If the remainder is not 0, it's odd. We don't do the jump. We do the odd case, multiply by 3 and add 1, and then we jump over the even case. All right. Lot going on here, but this is the core of the code. This will have to run each time. So not too many new instructions, lots of moves. That's what you'll typically see. You'll see lots of moves in an assembly program. Compare compares these 2 values. Jump equal jumps if they're equal. Div divides, mul multiplies, and they have that weird structure to them, but you can figure that out. Jump is an unconditional jump. And that's really all that's in here. All right. So now we need the while loop that surrounds it. So we need another register. And let's use RSI. And it will hold the stopping time. So every time we go through the loop, we will increment RSI. We'll add one to it. And if you look over here, you'll see we initialize it to 0 up here, move 0 into RSI. Then down in here, we will add 1 to it. Okay. And then we'll do that big if then else we built earlier. And then we'll jump back to the top. So here's our loop. It's a while loop, so we're going to run until RAX is 1. So the first thing we do up here is we compare RAX to 1. And we jump if it's equal to done. So we see is RAX, our current value 1. If it is, jump down to done, and we'll exit down here somehow. Otherwise, add 1 to our stopping time. Do that if then else, right? If it's even, divide by 2. If it's odd, multiply by 3 and add 1. And then jump back up to the top. So here's our loop. Again, nothing really new here. Move, compare, jump if equal, add, and then unconditional jump. We saw all those in the previous section. We need to initialize RAX to the value we want. We'll just pick one. 27 is a good one. We'll just put 27 in RAX, and that'll be the first thing we do up here at start. Right? So we'll say global start. The while loop we just wrote will go here. When we're done, we go to done. What happens at done is we exit. This is how you call the exit system call. And the way that the exit system call works is the exit value of the program should be in RDI. Now, if you go back one, you remember we went ahead and used RSI for our stopping time. So before we exit, we need to take RSI and move it into RDI. So it's going to be the exit value for the program. And then we're done. Whew. We put all of that together, and this is our program to compute the stopping time of 27. And we should be able to assemble and link it and run it. And in fact, pop down here. We can do all that, right? So we assemble it with NASM, and we link it with LD. And then if we just run it, it just runs. The result is in the exit value, which we can see this way, and we see that it's 111. So it takes 111 steps for that number to converge to 1. Is that the correct answer? There's actually an online calculator for the callouts conjecture here. If you plug in 27, you'll get 111. So yay, this works. You should walk through this. You should be sure you understand all the pieces of this. These are some very, very common instructions with a couple exceptions. Div is really uncommon to see in a program. It's really uncommon to see div in assembly. It's in there, it's used, it's just somewhat uncommon. And the reason is it tends to get eliminated by optimizations. And that's great because div is nasty. So there are some optimizations we can make in the program, and bitwise operations are great. The processor can do these really, really fast. It has specialized hardware called barrel shifters that can make these kind of operations nearly instantaneous. And so the div instruction is a really good instruction to take a look at because it's both complicated and obscure, and it's also very, very slow comparatively. So there is an instruction called SHR or shift right. There's also an SHL or shift left, but shift right is the one we want. Shift right takes the contents of memory or a register and it shifts all the bits to the right. And it puts a 0 in up here at the top, so 0 goes in. The 1 here at the bottom, that's going to come out, and we store that in the carry flag. So if you think about a base 10 number, like 100, if I shift the digits to the right, I'm dividing by 10, right? 100 becomes 10. Well, if I have a binary number, shifting it to the right one place divides by 2. Well, that's great. That's one of the things they wanted to do was divide by 2. And this is way simpler than using div, right? So we could, to divide it by 2, shift right once, and that divides it by 2. We can check the carry flag. That's going to be 1 if the original number was odd, and it's going to be 0 if the original number was even. Great. So that's one way to do that. There's actually a better way to test if the number is odd or even. And you'll see this in programs quite a bit. It comes up a lot. There's an instruction called test. So the test instruction takes 2 arguments, and it performs a bitwise AND on them. So, for example, here's 1. It's got a bunch of stuff in it. The value is 837. We AND it with this, the value 1. And you already know from your basic programming classes that 837 bitwise ANDed with 1 just masks off this low bit, and we'll get 1 if it's odd and 0 if it's even. And even better, it will set the 0 flag for us. So 837 bitwise ANDed with 1, since this is odd, is going to result in a 1 at the end here. That's not 0. So the 0 flag is not set. It's 0. Confusingly, if this had been 0, this would be 1. And so now I can use test, and I can use the jump if 0 to check for even or odd. And we see that a lot in programs. Test REX1 is a quick way to check if something is even. We also see it used like this. And you'll see this a lot in programs. I want to know if REX is 0. And so I AND it with itself. And I will get 0 if and only if it's 0. If you think about that, ANDing it with itself means that if there's a 1 in this position, there'll be a 1 in this position. 1 and 1 is 1. And so I'll get non-zero. I only get 0 when RAX is 0. So you'll see test a register with itself. That is a way of checking for whether or not that register is 0. It's faster than comparing it to 0 because it uses fewer bytes, takes up less space in a pipeline, and just gets optimized by the processor. All right. If we make those substitutions, over on the left is the original program, which has, if I can get the mouse to work, div here and div here. So this case is easy. I just want to take RAX and divide it by 2. I will just shift it right once, and that will do it. Div gone. This is a little more complex. I want to know if RAX is even, and if so, I want to jump to even. Well, here I will test RAX, 1, and then jump if 0 to even. Take me down here. So the great part about this listing over here is that the div instruction is gone, which is great because in case you hadn't noticed, div is annoyingly complex. Div's gone. I don't have to set RDX to 0 anymore or any of that. I just do this quick shift operation. And so that is how this guy works. Are there questions about this before I move on? Great. You all are shockingly quiet, which I assume means this is super intuitive and you've all got it. There is more we can do. So if we go back here, you'll see we're adding 1 to RSI. This is slightly less efficient than using a special additional instruction called increment. I can increment RSI a little faster. It turns out I can get rid of the multiply by 3 and add 1. There is a dirty trick that I will cover in a future class using an instruction that looks nothing like that called load effective address. Yeah, again, this makes this there's no connection here. Load effective address, which is commonly used to do this kind of math very fast. And you typically don't do things in assembly like this. Put a 0 in RSI. You don't do that. For efficiency, you use exclusive OR to set something to 0. We'll cover these kinds of things later, but there are things that you will see in assembly, and you sort of have to understand what's going on. You need to recognize these common idioms because if you just looking at assembly and you run across some of this stuff, you may be completely baffled as to why they're exclusive ORing a register with itself, testing a register against itself, even looking up the definition of these instructions won't necessarily tell you what the intent is. So you have to see some of this stuff. If you ever become a malware analyst, which some of you may, you see intentional obfuscation in assembly, and that can be really gruesome. And so that's when you really need to fall back on automation so that it can tell you what's going on without you having to make bad assumptions. So what did we learn here? Build parts of your program in pieces, get each piece working, and then optimize it later on, right? We just did the dumbest thing with the fewest instructions, and then we went and added the crazy optimizations once it was working. And that's true in general. That's how you should write your C code or your Python code, get it working, and then add the optimization, right? Premature optimization is a bad thing. The other thing we learned is that the right way to do something in assembly isn't always the same as in a higher level language, right? In assembly, I want to use shift operations. I want to use bitwise logical ands because they are very, very fast, and that's going to give me a good result. In a high level language like C or Python or Rust, I'm probably not going to do that. I'm going to let the compiler figure it out for me. And the compiler will probably do what we did in assembly. Okay. Let's shift gears a little bit and talk about how compilation works. So I start out with a simple piece of code like you see up here. Here's my simple function, int simple, takes an int, returns that int, super uncomplicated. In fact, most compilers will optimize that away because they like to throw code away. Compilers love to, if they can figure out some obscure reason to throw your code away, they will throw your code away. They love doing that. All right, the fastest code is the code you never run. So when we put this through a compiler, the first thing that most compilers do is convert it to an intermediate form. And that intermediate form is almost always a register transfer logic, RTL. And so here, this is the RTL that's generated for our little function. And it's got a lot more stuff going on in it. There's a lot of craziness in here. What all is actually happening? Well, it adds a bunch of information about, for example, the size of an int on our platform, right? It's a signed 32-bit integer. There's some additional odd stuff here. It tells us about storage. It introduces these intermediate values where it allocates some storage. It tells us how that storage has to be aligned in memory, aligned on the 4-byte boundary. It tells us more about the implementation. And it tells us eventually what the return value in this case a 32-bit integer, is it's going to be this value 6. 6 is here. You see what it is? It involves 4. We can go back up here. We can trace through this and figure it out if we really want to. I don't really want to. Once you have this intermediate form, that's great because you can now convert it to assembly language. So up here, this was in C. This is in an RTL. And once I've gotten to RTL, I no longer care that this was C. This could have been Rust. This could have been any other language. Once I have turned this into RTL, then I can use any backend to write it out to assembly. Assembly for the x86, assembly for ARM, whatever. I'll convert this into the appropriate assembly. So this is great. It divides up the work the compiler writers have to do. If I want a new language, I have to not write a compiler to get from source all the way down to assembly. I write a compiler to get from source to RTL. And I'm done. Somebody else has done the hard work of getting RTL into assembly, and that's great. If I need a new assembly language, if a new processor out there or something's added to the processor, somebody will go and fix this error right here of converting this into better or new or different assembly. And that's great. You want to support a new processor like AVR, you need this pipeline right here. No changes have to be made up here. In the ideal, in the absolute best case, that's the way that's going to work. So here's the assembly. The assembly down here is not in Intel. It's in AT&T because this is done using GCC. But you can see there's the branch protection stuff. There's some assembler directives in here that sort of take up a little bit of space. We do the push. There's a move. This is sort of pro forma. We'll talk about this later on. The pop down here. We put some stuff in memory and move it around. And basically, if you trace through all of this, again, nothing happens. We just end up with the incoming value in EAX and return. Simple stuff. Finally, we convert it to a .o file, an object file, and that ends up looking like this down here. And you can do all these steps yourself from the prompt. They're just different switches you provide to GCC to see different stages of an intermediate form. I think actually one of these I stole from LLVM because it's way shorter and I wanted to fit it on a slide. But there you go. All of these are useful. So if you happen to have source lying around and you can get it that way, that's great. But these intermediate representations, these IRs, these things that live between your source and your object are all useful. Assembly is one we'll use the most, but a lot of times things can be pretty obscure in assembly, and you can lift it to something like an RTL. You can do your analysis up here, and there are lots of tools that do exactly that. They will create a purpose-built intermediate representation and use that to do some analysis, and we'll see some of that. The reason is the semantics of this can be problematic. Things like div, for example, have some problematic semantics. Up here, we can make those semantics more obvious and structure it in a form that can be passed to things like theorem provers or model checkers, etc. Okay. Whew. Well, that was a lot. I actually thought there was more in this lecture, but I think I actually moved that to the next lecture because I felt like there was too much in this one. There's homework. It's Wednesday, so there's new homework. The new homework is for you to write some assembly. It's due in 1 week. When you have questions, please email me. What I want you to do is write some code that computes the Hamming weight of a binary number. That may sound ugly, but it's not too ugly. You may already know what Hamming weight is. It's something that shows up in computer science all the time. The Hamming weight of a string is the number of symbols that are distinct from the 0 symbol of the alphabet used. So if it's decimal 100, the Hamming weight of that decimal number is 1. There's a single non-zero digit in there. For a binary digit like this, a binary number like this, it's just the number of ones that are present in that number. And it turns out to have interesting applications. You can look it up on Wikipedia and you can see. So the Hamming weight for the number, the hex number 21A436 Foxy is 16 because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. That's it. Here's some C code that computes it. The C code says initialize the weight to 0, run 32 times. Each time, take the weight and add the value bitwise ANDed with 1. And then shift the value to the right once. So we're doing bit shifts and bit tests. So that probably implies a way for you to do this. You just have to create a loop that runs 32 times and then put this stuff inside it and then return the weight. Your homework is to write an assembly program that computes the Hamming weight of a number. I'm not expecting you to start from 0. I'll give you a bit of a start. So this code should be available. I believe it's available up on the assignment page. It has this little make line if you want to use it. If you don't, you ignore it. It defines start to be global. It creates the section text. The order of these instructions does not matter. How do you want to do it? Comments introduced with semicolons. In NASM, not everywhere. They're introduced with pound symbols in the GNU assembler, but here the comments are introduced with semicolons. Here's a little macro, percent define input to be this number. The automated checker I've written is going to look for this line. It's going to look not for this number, but it's going to look for percent define input. And when it finds that, it's going to go ahead and modify this so it can try other numbers. So please don't change this too much. Here's your start, your entry point. I put input, which is really going to be this number, into RAX. And then I compute the Hamming weight by some tricky means. And at the end, I make sure the Hamming weight is in the register RDI, because that's going to be the exit value of the program when I call the exit system call, which I do right here. Here's a hint. Maybe, again, if you want to do a bit test and look at the carry and then shift it, that'll work. But there is an additional instruction you might want to know about called add with carry, ADC. And what it does is it adds a number to a register, and then it adds the content to the carry flag. So if we did add with carry REX and, 7, it would add 7 to REX and then add the carry flag, which would be a 0 or a 1. So you might want to think about that. There may be something you can use with this instruction, right? In the C code, there was an add. That's sure, there was that. So I don't know, maybe there's something you can use here. You'll need to check all 32 bits. I want to work with 32-bit numbers. So you want a loop that runs 32 times. And then you should be careful what you choose to store in each register. There are a couple common mistakes people make when they start to write assembly. One is they overwrite registers, sometimes accidentally, occasionally implicitly, right? If I use the div instruction, I will overwrite RDI, and I may not know I'm doing that. And weirdly, I might get an exception and wonder, why am I getting an exception? And I'll get the weirdest part about it is, and I recommend you try this out, remove that line of setting RDI to 0 and try it out. You get a floating point exception. There are no floating point operations in the code, just the way that Linux decides to report it. So be careful what's stored in each register. Pay attention to the control flow of your program, but otherwise, I think you have all the tools to do this. This problem is, I believe, much simpler than one we just went through. So go through the code we just went through. Be sure that you really understand that. And then I think you can do this. You have a week to do it. Send me questions that you have, and I'll try to answer them. One thing I didn't mention in the past that I'll mention now, if you turn your homework in early, and if I have time, I may go ahead and look at it and grade it. And if I do that and you don't like your grade, you can turn it in again and I will grade the new stuff. So if you do it early and you turn it in and I have time to look at it, I may look at it, grade it, and then you have, and if you don't like that, you get another chance before it's due to fix the problems. All right. All right. Next time, more assembly.